Our next method is Newton-Raphson method. This is most important topic from this chapter from gate point of view. So here also our aim is we have to solve this equation fx equals to 0. Initial guess is x equals to x naught. And we have to see what should be the formula for first approximation, second approximation and so on. See the one basic difference between the other three methods that we have learned till now, bisection method, regular-Falsy method and secant method. In all the three methods, we had to solve this equation in some given interval AB, right? Some interval AB was given, and in that interval we had to solve this equation fx equals to 0. And this interval AB was such that at one point the value of f of x was negative, at other point this was positive. Now here in Newton-Raphson method, only one point is given. The initial guess is given that x equals to x naught is the root, and from this initial guess we have to find the actual root using this iterative method. So first we are going to see what is the approach in case of this Newton-Raphson method. In bisection method we were calculating the midpoint. In regular-Falsy method and secant method we were joining the points A and B by a straight line, and the point where the line was crossing the x-axis, that was our first approximation. Now here suppose if this is the graph of the function y equals to f of x, the point where the graph is crossing the x-axis, this is actual root alpha. Now here in order to calculate, this is the first approximation x naught. Approximately we are saying that this is the root, and the corresponding point on the curve is x naught and the value of y is f of x naught. This height will be f of x naught. Okay, this height will be f of x naught. Now in this Newton-Raphson method what we do, that we draw a tangent line at this point A. Okay, we draw a tangent to this curve y equals to f of x, and suppose if this is the tangent line, then point where the tangent line is crossing x-axis, this is our first approximation x equals to x1. Okay, we are drawing a tangent at this initial guess point. Initial guess was x naught, corresponding point on the curve was this point A. And here we are drawing a tangent line. The point where the tangent is crossing x-axis, this is the first approximation x1. Now for the next iteration what we will do, that we will find the corresponding point on the curve. We will again draw a tangent line at this point. The point where this tangent will cross x-axis, this will be our second approximation x2. So in this way you can see that we started with this initial guess x naught. This was our first approximation, second approximation. So with each iteration we are getting close to this actual root alpha. Okay, and if the more accuracy that we want, the more number of iterations we have to perform. But you can see that with each iteration we are getting closer and closer to this actual root. So this is the basic idea behind this Newton-Raphson method. Now our aim will be, we have to find the formula to calculate this x1. Okay, the formula for calculating x1 in bisection method was a plus b by 2. In regular-Falsy method, x1 was a f of b minus b f of a by f of b minus f of a. The same formula was also there in case of secant method. So now we are going to see what should be the formula for x1 in case of Newton-Raphson method. So here what we have to do, we have drawn a tangent at this point A. So we have to write the equation of this tangent line, and the point where this tangent line will cross x-axis, this will be our first approximation x1. So to find x1 we have to write the equation of tangent to curve y equals to f of x at this point A. Okay, at this point A we have to write the equation of the tangent line. Now we know that the equation of a straight line is y minus y1. This equals to m into x minus x1. This is one point form of the line. So x1, y1 is the point through which the line is passing, and m is the slope of the line. So here the line is passing through this point A, x naught, f of x naught. So this means the equation of the line will be y minus, in place of y1 we have f of x naught, and this will be m. Now the slope of tangent we know is nothing but the value of first derivative, right? The slope of tangent will be dy by dx at this point A. So this you can write as f dash x naught. F dash will mean first derivative, and if we calculate f dash at this point x naught, then this will give us the slope of this tangent line at point A. So in place of m we can write f dash x naught, and here we'll get x minus x naught. So this will be the equation of tangent line at point A. Now To find the first approximation x1, we can see that when x is x1, the value of y is 0. When x is x1, the value of y is 0 because point x1 is on the x-axis. So now in this equation of this tangent line, in place of x I will write x1, in place of y I will write 0. So we'll get 0 minus f of x naught, and this will be f dash x naught. In place of x we have to write x1, so x1 minus x naught. And if you rearrange this, then you will find that x1 will be x naught minus f of x naught, and this divided by f dash x naught. So this is a very simple formula to find x1. x1 will be x naught minus f of x naught, and this divided by f dash x naught. So the formula for first approximation is this, you have to remember, x naught minus f of x naught, and this divided by f dash x naught. So this will be the formula to calculate first approximation. Now for the second approximation x2, you have to replace this 0 by 1. So we'll get x1 minus f of x1, and this divided by f dash x1. And the general iterative formula will be xn plus 1. This is xn minus f of xn, and this divided by f dash xn. So this is the formula to calculate the next iteration in case of Newton-Raphson method. Now after this we'll take a number of problems and we'll see how to apply these concepts. Okay, so this is our first problem on Newton-Raphson method. We have to solve this equation fx equals to e to the power x minus 1 equals to 0 using Newton-Raphson method in 3 stages with initial guess x naught equals to 1. Okay, so here the function that is given to us is fx is e to the power x minus 1 f dash x. This will be e to the power x. Now the formula for, and also the initial guess that is given to us is initial guess x naught is 1. Now for the first approximation, the formula was, for first approximation the formula was x1 is x naught minus f of x naught, and this divided by f dash x naught. So here x naught that is given to us is 1 minus f of 1 by f dash 1, right? Now this is your expression for f of x, e to the power x minus 1, and f dash x is e to the power x. So this will be simply 1 minus f of 1, so this will be e to the power 1 minus 1, and this divided by f dash 1, f dash x is e to the power x, so this will be e to the power 1. So if you take LCM, then e minus e will cancel, you will get 1 by e. 1 by e is 0.3678. So this will be the first approximation x1, 0.3678, or you can approximately write this as 0.368. Okay, so this will be our first approximation, 0.368. Now we have to calculate the second approximation. So for second approximation, the formula will be x2 is x1 minus f of x1, and this divided by f dash x1. So now our x2 will be, in place of x1 we have 0.368. Okay, in place of x1 we have 0.368 minus f of x1. So f of x1 will be e to the power 0.368, e to the power 0.368 minus 1, and this divided by e to the power 0.368. So this will be our second approximation x2. Now if you do the calculation, you will find that this will be 0.05, I guess. Okay, you can perform the calculation and you will find that this number will be 0.05. So this will be our second approximation x2. Now for the third approximation, x3, this will be x2 minus f of x2, and this divided by f dash x2. So now in place of x2 we have 0.05. This is your expression for fx and f dash x. So this will be 0.05 minus e to the power 0.05 minus 1, and this divided by e to the power 0.05. Now again if you do the calculation, this number will be 0.01. Okay, so after 3 iteration you will find that the root is approximately 0.01. x3 will be 0.01. The question was we had to find the root in 3 stages. So this will be the answer, 0.01. Now we are going to see what happens. We are going to see the graphical explanation for this thing, that what is happening with each stage. This was our second approximation x. Let me write all the approximations that we are getting. Initial guess was 1, x1 is 0.368, x2 is 0.05, x3 is 0.01. This is our answer. Now let me draw the graph, and with the help of graph, let us see what is happening with each iteration. In that way you will have a better understanding of this Newton-Raphson method. Say these are our coordinate axes. This is x-axis and this line is y-axis. Now we all know that the graph of this function y equals to e to the power x will be something like this. This will be an exponential graph of this exponential function, is an increasing graph when base is more than 1. Now this point obviously is, if you place x equals to 0 here, the value of y that you are going to get is 0, 1. Now if we are interested in drawing the graph of e to the power x minus 1, so this means we have to shift the graph of y equals to e to the power x by 1 unit towards negative y-axis. So this point 0, 1 will become 0, 0. So now the graph will be something like this. This will be your graph of y equals to e to the power x minus 1. And as you can clearly see that the point where this graph is crossing x-axis, this point is origin 0, 0. So this means actual root is x equals to 0, and this you can verify from here also. If you place x equals to 0 here, then e to the power 0 will be 1, 1 minus 1, 0. So this means the actual root of this equation, actual root alpha is 0. We started with the initial guess of 1. Initial guess x0 was 1. So initially we guessed that the root of this equation is 1. Now the first approximation was 0.368. Now graphically, what is the meaning of this? This means if we draw a tangent line at this particular point, then the point where this graph will cross x-axis, this will be x1 and this was 0.368. Now in the next iteration what we had to do, that we find the corresponding point on the curve, again draw a tangent line. The point where this tangent is crossing the x-axis, this will be our second approximation, x2. x2 was 0.05. For the next approximation we are finding the corresponding point on the curve, again draw a tangent line. This will be our third approximation, x3, 0.01. So as you can see, now this x3 is very close to the actual root alpha, right? x3 is 0.01, actual root is 0. So the third approximation is very close to the actual root. So with each iteration what is happening, that we are getting closer and closer to the actual root. Initially our guess was 1, so this means error will be 1 minus 0. Now our second approximation, our first approximation was 0.368. So now this will be the error. So with each iteration we are getting closer and closer to the actual root, and the error is gradually being reduced. So this is the basic idea behind this Newton-Raphson method. Now we are going to take some more problems on this Newton-Raphson method, and we'll see how to apply these formulas. We are going to take 2 more problems on this Newton-Raphson method. Both of them were asked in GATE previous year papers. One is from GATE 2016 Civil Engineering, another one is from GATE 2015. So the first question is, Newton-Raphson method is used to find the root of this equation. So this means our fx here is, fx is 3x minus e to the power x plus sin x. This is f of x. If the initial guess taken is 0.333, initial guess x0 is 0.333, so this is our initial guess. Now the question is the next approximation will be, so the problem basically is we have to find the value of this x1. Okay, the function fx is 3x minus e to the power x plus sin x. x0 is given, we have to calculate x1. Now we know that in formula for x1 we'll need the expression for f dash x. So if this is fx, f dash x will be 3 minus e to the power x, and derivative of sin x will be cos x. So this is f dash x. Now x1 will be x0 minus f of x0, and this divided by f dash x0. The value of x0 that is given to us is 0.333 minus f of x0. This is your f of x, and in place of x you have to write this x0. So this will be 3, in place of x0 we have 0.333 minus e to the power 0.333 plus sine 0.333, and this divided by f dash x naught. Now this is your expression for f dash x. In place of x we have to write 0.333, so this will be 3 minus e to the power 0.333 plus cos of 0.333. Now after this you have to perform this calculation, and while performing the calculation remember one very important thing, that here this angle 0.333 is not in degree, this angle is in radian. So this means you have to turn your calculator in radian mode and then you have to perform the calculation. Okay, remember that if sine 1 is given, so this sine 1 is not equal to sine 1 degree, right? Sine, if simply sine 1 is given, this means this is sine 1 radian. Okay, so here also if nothing is given, this means this angle is always in radian. So while performing the calculation your calculator must be in radian mode. So if you do the calculation correctly you will find that this number will be 0.36. so this will be our first approximation x1. Okay, so this was fairly simple question. The formula is also very simple. x1 is x naught minus f of x naught and this divided by f dash x naught. So our first approximation x1 is 0.36. The question was we had to find the next approximation, means we had to find the first approximation. So our answer will be 0.36. Now the next problem is, this is also a very simple question. In a Newton-Raphson method, initial guess x naught is 0. The given function fx is minus 2 plus 6x minus 4x square plus 0.5x cube. The correction factor to be added in x naught to get the first approximation x1 is, so correction factor delta x, this means we have to find x1 minus x naught, right? The question is what should be added in x naught to get x1. So this means we have to find x1 minus x naught, and as x naught is 0, so this means this will be x1 minus 0. So delta x here will be simply x1. So the problem basically reduces to we have to find the first approximation x1. As x naught is 0, x1 minus x naught will be simply x1. So now if this is f of x, f dash x will be, derivative of constant will be 0, derivative of 6x will be 6 minus 8x plus 1.5x square. So this will be the expression for f dash x. Now the formula for x1 will be x naught minus f of x naught and this divided by f dash x naught. X naught was 0, so 0 minus f of 0 and this divided by f dash 0. So this will be 0 minus, or we can simply write minus f of 0. This is your expression for f of x. In place of x, if we substitute 0, then we will simply get minus 2. So this will be minus 2 and this divided by f dash 0. This is your expression for f dash x. In place of x, if we write 0, these two terms will become 0, we'll get 6. So this will be 2 by 6, 1 by 3 or 0.333. So the answer to the second question will be 0.333. We had to find the correction factor. Correction factor simply means x1 minus x naught, the difference of these two consecutive roots. Since x naught was 0, so this means delta x will be simply x1. Okay, x1 minus 0, so delta x will be x1, the value of x1 is 0.333. So for the first problem the answer is 0.36, for the second one the answer is 0.333. Okay, so till now we have discussed 4 different methods for solving any algebraic or transcendental equation. The first one was bisection method, then regular falsy method, secant method and Newton-Raphson method. So now we are going to see some important points related with those 4 methods. Regular falsy method and secant method was basically same except for that one minor difference. So the first point that we have to remember is, in this table we have to remember there were 3 different methods: bisection method, regular falsy and Newton-Raphson. Regular falsy and secant were almost similar. So bisection method is slow, regular falsy method is also slow and Newton-Raphson method is fast. So the meaning of this thing is that in these 2 methods, bisection method and regular falsy method, you have to perform more number of iterations to get the actual root. Okay, there is one term called order of convergence which is used to represent the order there is one term called degree of convergence or order of convergence, which is used to define whether a method is fast or slow. So order of convergence for this bisection method is 1, regular-Falsy method is 1, and Newton-Raphson method is 2. So this means in case of regular-Falsy method, you have to perform half number of iteration compared to these two methods to get the actual root. Now the second important point is these two methods, bisection method and regular-Falsy method, these two methods will always converge. Always converge means we will always get a root of fx equals to 0, because remember that in these two methods we were always making sure that f of a into f of b is negative. So this means between a and b we will always get one root of fx equals to 0. But this Newton-Raphson method, even though this method is fast, but one of the problem with this Newton-Raphson method is sometimes this method may diverge, meaning that we may not get the actual root using Newton-Raphson method for some function. For example, one case you can easily see that the formula for x1 was x naught minus f of x naught, and this divided by f dash x naught. Now suppose if this f dash x naught is 0, then what will happen? Then this method will fail. We will not get the actual root using this Newton-Raphson method. Another possibility is, suppose if the graph of this function is something like this, y equals to fx, this is the graph of function. Now the point where the graph is crossing the x-axis, this is the actual root alpha. In Newton-Raphson method, what we are doing, that we are drawing a tangent line at this point. The point where this tangent will cross the x-axis, that will be our first approximation. So if you draw a tangent line here, the point where this line is crossing x-axis, this is your first approximation x1. Now for the next approximation, we have to find the corresponding point on the curve. Then we have to draw a tangent line here. Now if you draw a tangent line here, you can see that this tangent will cross the x-axis somewhere here. So this will be the second approximation x2. So you can see that what is happening with each iteration, instead of getting closer to this actual root, we are getting away from the root. Okay, this was our initial guess, then first approximation x1, then second approximation x2. Now you can see that if you want to find the next approximation, you have to draw a tangent line here. If you draw a tangent here, you can see that it will meet somewhere here. So instead of getting closer to this actual root, we are getting away from the actual root alpha, and this means we will never get the actual root using this Newton-Raphson method for these type of graph. So therefore this method may diverge sometimes. So that is one of the problem with Newton-Raphson method. Even though this method is fast, the formula here is also very simple. The formula for x1 is this formula. So you can see that this is very simple formula. But still the problem is that this method may diverge. So this table you have to remember, bisection method and regular-Falsy method will always converge. This means you will always get a root, but in Newton-Raphson method you may not get root in some cases. And the second one is a formula which you have to remember, the minimum number of iteration required to solve fx equals to 0 in this interval a to b with an accuracy of epsilon using bisection method is given by this formula, b minus a by 2 to the power n is less than epsilon. Using this formula you can find the minimum number of iteration n to solve this equation fx equals to 0 with an accuracy epsilon. Accuracy epsilon means the root will be always between, if the actual root is alpha, then you will get alpha, then the root that you are getting after n number of iteration will lie in the interval alpha plus epsilon to alpha minus epsilon. So these are the 2 points that you have to remember. This formula you have to, one important thing about this formula is independent of this function fx. Notice that you have only this end point a and b, and number of iteration n, epsilon is the accuracy. So we'll take one problem and we'll see how to apply this formula. So this is the next problem based on this formula that we have learned just now. This question was asked in GATE 2017 in electrical engineering. So the problem is only one root of fx equals to 0. Fx is x to the power 6 minus x minus 1 equals to 0, lies in this interval 1 to 2. Now the question is, find the minimum number of iteration to solve fx equals to 0 with an accuracy of 0.001 using bisection method. Remember that this formula is for bisection method only. Okay, so and this formula is independent of the function, so this expression is not required. Okay, the formula is independent of this expression for fx. So the minimum number of iteration will be given by this formula, b minus a by 2 to the power n is less than epsilon. In place of, this is your point AB, in place of a you have 1, in place of b you have 2. So 2 minus 1 by 2 to the power n, this will be less than epsilon. Epsilon is 0.001. So this you can write as 1 by 2 to the power n less than 1 by 10 to the power 3. Now remember one thing, in case of inequality, when you take reciprocal, then you have to change the sign of inequality. Okay, because suppose if 5 is more than 2, this we know. Now if you take reciprocal, then 1 by 5, 1 by 2, which one is greater? 1 by 2. So once you take reciprocal in case of positive numbers, then you have to change the sign of inequality. Greater than will become less than, or less than will become greater than. So here if I take reciprocal, then I will get 2 to the power n greater than 10 to the power 3, means 1000. Now we all know that 2 to the power 9 is 512. 2 to the power 10, this will be 1024. This you have to solve using heat and trial method. You can also solve this by taking log on both sides, but heat and trial method is also equally valid. So 2 to the power, if we take n equals to 10 here, okay, then 2 to the power 10, this will be more than 1000. 2 to the power 9 is less than 1000. So this means the value of n will be 10. Minimum 10 number of iterations is required to solve this equation fx equals to 0 in the interval 1 to 2 using bisection method, such that we'll have an accuracy of 0.001. So the answer to this question will be n equals to 10. Now, so this was the last problem on this topic. Now after this we have to learn numerical integration.